starting? There. Okay, so basically this last part is this last test is 2 topics only, okay? There's 2 different sets of word problems, the ones we're starting today, and then we're going to learn how to set these problems up so that we can solve them, and then there'll be an identical sheet with the questions slightly changed to actually be more realistic, and then we're going to learn a different way to solve those ones. So it's sort of 2 types of word problems and how to solve them. They're not hard. Okay, so that's one thing. They're not hard. Did anyone take linear algebra? You did? Oh, yeah. So it's systems of equations. It's like matrices for this first type, and then the second type is graphing equations. So we're going to learn how to solve them after we learn how to set them up. So we're going to set these ones up, these 5 tonight, and then we'll just see if there's time we might learn how to solve one or talk about how to solve them. Next class we'll solve them, and if you miss next class, then it's really going to be hard to do it. I find you have to be here and try them along with me, and then you'll get it. If you just look at notes or something, it's really hard to look at the notes and know what I did first, second, third, right? But if you're watching it and doing it along with me, then they're actually really easy. All right, so this is the type of problem that we're going to learn how to solve. So let's read the first one. Everyone has a sheet? A shop sells 2 types of television sets. The deluxe model sells for $1,100 and the regular model sells for $700. TVs now are cheap. Did you guys see that? I was in Walmart the other day and there was a 60-inch TV and it was like $300. TVs used to be like thousands.
Yeah.
Like they're not now. They're really cheap.
55 smart TVs for like $405.
Yeah.
Like there's nothing.
I know, and you know my parents, so microwaves are relatively cheap, but my parents said when they bought a microwave first, they had one of the first microwaves, and it wasn't even digital, you had to turn a knob and stuff, that it was $1,100. They would have bought that probably in the 80s or something, or maybe 70s. It was like $1,100. And what's a microwave now? Like $100? You can get them for really cheap, right? A couple hundred if you wanted a bigger one. So I'm just looking at this price, and I just saw those TVs at Walmart. I said, I can't even believe how cheap TVs are now. The entire stock is worth $138,000, but only 1/3 of the deluxe model and half the regular models are sold, for a total of $55,500. How many of each type of television did the shop have in stock before the sale? Okay, so let's write all this information down. So there's 2 types of television sets. Deluxe model, so let's call that D. And it sells for $1,100. And the regular model is $700. Okay. Okay. I meant to write notes on how to do it, but we'll kind of just do the first one and then I'll write that down. So the entire stock is worth $138,000. Okay, so if D is the number of deluxe models, okay, that they have in stock, so let's just write that down. This would be like the number of deluxe model in stock, and R would be the number of regular models. right. Now, if we multiplied 1100 times D, what do we get? Like if D was 10, if there was 10 TVs, we multiplied by 1100, that's the value. That would be how much that's worth, right? And it says the entire stock is worth this. So what would we do to get the entire stock? Plus 700 times R, do you agree with that? So if we multiply that by how many TVs we have of the deluxe model, that would be the value of those ones. Add 700 times however many regular TVs we have, then altogether that is equal to 138,500. Does that make sense? So what's the next piece of information they give? So this is the value of them, but this is telling you about their sales, that they sold a third of them. So how could you change that? If we said a third of the whole value of the deluxe models, and how much of the regular? 1/2 of them equals 55,500. Right, so instead of the whole stock, a third of it and 1/2 of the other, and then if we added those together, that gives us our sales. So these would be our equations, and we would want to solve for D and R, and it would tell us how many there is. So how do we solve for D and R without what I said we're going to do, linear algebra, but this one we can actually just solve. So any ideas how we would solve that? So let me show you an easier equation, okay? So a system of equations okay, let's start with one equation. Tell me an answer to that. An answer. What would work if we knew X and Y? What would work?
2 and 2.
Okay, 2 and 2 is one answer. Another one.
1 and 3.
Yeah, or 3 and 1, 5 and -1, right? Those would all work. Those are all called solutions, right? So every line itself or every equation would have infinitely many numbers that we can plug in, okay? So this line just by itself, there's not infinite number of answers because we can't have negatives because it's a word problem. But if there were 0 of these, then R could be something that would 700 times that if it worked out nice. So we wouldn't want decimals either. Here we could have decimals because I'm not giving any criteria. We could say 3.5 and 0.5. That doesn't work up here for word problem. It's more rigid, right? You can't have negatives. You can't have decimals, fractions of a TV, right? So when we then add another equation, let's say x minus y equals 2. So now this is called a system of equations when there's more than one equation, and a solution has to work in both at the same time. So what solution, just looking at them, will work in both? One of the ones we listed. No, because 2 minus 2 would be 0. 3 minus 1 is 2, and 3 plus 1 is, right. So the solution would be 3,1, the point 3,1 if we wanted, or we could say x equals 3 and y equals 1, which is more like what we're going to do, because we're always going to answer these word problems, so if these were TVs or something, then you could say that. So we could look at that one and solve it. This one we can't look and solve. So there's methods to do that, okay? So the method that we're going to use to solve a system with 2 variables It means two letters. In ours is R and D, or this one was X and Y. We will use elimination. Okay, so let me just show with numbers that aren't so big and weird as that one to start. Okay, so I'm not ready for this. I'm straying from what I wanted to do, so just give me a second here. They're going to work out to weird numbers because I don't have them ready, so they'll be decimals or fractions, right? So, but that's fine. Okay, so here's two equations, and suppose we want to solve for X and Y. Does anyone remember how to do this or have an idea what we might do?
Would you multiply, like, say if you multiplied find a common denominator or something?
Yeah, kind of like that, not a denominator because they're not fractions, but fine,
But, like,
yeah.
if you were trying to get minus 2y or whatever, would you multiply the top by minus 2 or something like that? Or
Yeah, so we're going to eliminate either the X or Y. Say we want to eliminate the Y, and I would choose the Y for a couple of reasons, but you actually want them to be different signs,
Okay.
so that when you add them, it'll disappear. So this is a minus 2. What could we multiply the first one by to get a 2? So if we multiply the first equation by 2, then we'll have, multiply everything by 2, so we would have 4x plus 2y equals 12. And then we're just going to rewrite the second equation. And if we add them together now, we'll have eliminated the y from the equation. So what do we end up with? 4 and 3 is 7x. 2y minus 2y, they cancel, equals 17. So x equals 17 over 7. Right, 7x equals 17, divide by 7. Does that make sense? Now how would we find the y? One of them, it doesn't matter which one. Probably the first one is better. 2 times 17 over 7 plus y equals 6. And we could just put these as a decimal. So 1.14, this is 2.43. So you could write it as a point, or you could just leave them separate. Okay, so that would be the numbers that would work in both equations. Does that make sense? So let's just put another elimination question, and then we'll solve the word problem itself that we had. Again, they're not going to work out nice because I'm just making them up on the fly, but this is more likely what's going to happen. So the first one worked nice. We could just multiply the top equation by 2, then the y's could eliminate. This one, you have to multiply both equations to make the numbers the same. We can either eliminate the x or the y. I'd probably choose the y again because the signs are already different, but you don't have to. You could choose the x. So if I had to, if I was going to eliminate the y, I want the numbers in front of the y to both be the same. So 2 times 3 is 6. So I could multiply the first one by 2 and the second one by 3, and that would give me a plus 6 and a minus 6 for the y. Okay. What would be my other option? If I want to eliminate the x, what would I multiply by? 5 and negative 2, right, you want them to be opposite signs, so when you add them, they eliminate. Don't subtract equations, because then you get really minus a minus and some weird things, and you'll make mistakes, I promise. So we always want to add equations, so you put the minus sign right into it, then when you add it, it's gone. All right, so this would be 4x plus 6y equals 12, and the second one will be 15x minus 6y equals 3. Add them together. 19x, these disappear, equals 15. So x is 15 over 19. Now the word problems, they usually work out nice because they've been set up so that they work out nice, right? Plug this in to either equation. So I'm just going to write the first equation. So 2 times 15 over 19 plus 3y equals 6. To solve for y, move this over. So it'll be 30 over 19. So 3y equals 6 minus 30 over 19. You could put that as a decimal if you wanted to. And then what? Divide by 3. 6 minus 30 divided by 19. You could write them as a point or just leave them like that. Okay, do you sort of remember doing that from high school? Okay. So let's go back to our question. I'm just going to rewrite it. So question 1 on the sheet, we had it set up that we had 1100D plus 700R is equal to 138500, and the other one was 1/3. Oh, yeah. I'd probably put these together as a decimal, right? I would probably 1100 divided by 3. So I might rewrite this second equation as 366.67D plus 350R.
So you can make it fraction, or you can make it decimal right away in this one?
You can always in these, really, but you have to think about your answer. Like if you rounded off and you ended up with .1 TV, it probably was because you're rounding error, so you'd actually answer it. Yeah. It's better to leave everything as fractions always. It's more accurate, right? Because we wouldn't have rounded that off. But okay, so because these are going to work out nice, it's not going to work out to part of a TV. So, but our numbers should be close. Yeah. Okay, so let's line up our equations. What are we going to do to make something the same? Yeah, like what if we multiplied, actually, if we looked here, this might have been better. If we multiplied this one by, like, -3, then the third would have canceled anyway. Right? Like if we multiply this, the number, this is more obvious, the 2, but the 3 is probably better because then it gets back to the no fraction. Like if we multiplied this by -3. This will be back to 1100, negative 1100D, -3 times 350, and 55500 times 3. So probably I didn't need to do that. So third and or you could have multiplied by 2 and get the 700s to match. Okay, these are gone. This will be negative 350R. Oh, does this give me a negative?
On the other side, negative. Oh, that's not.
Oh, I have this number wrong. Oh, no. What did I... Do I... Yeah. 3 times 55500. Oh, there should be a 1 here. There we go. So what would R be? Divide by negative 350. And then how would we find D? Plug it into either equation. I'm going to do the one without the fractions in it. Plug the R in. Right, and like I said, with the word problems, they always work out that the answer will make sense. If you end up with some weird decimal, then you could go back because you probably did something wrong. Right. So what did the question actually ask? We want to make sure that we answer any word problems with what they're asking for. How many of each type did the shop have before the sale? So, and those were the R and the D before the sale. So, before the sale, they had 80 regular, was it? And 75 deluxe. So I set up those equations without, just by telling you, but how are you going to be able to do that just by looking at them? So what we usually will do is sort of make a table. So to set up word problems. So one, you're going to obviously read the problem. 2, we're going to write down the question or underline the question. So what it is they're looking for in the end. So basically you want to think about, if I, like in this last one, it said, how many of each TV did they have? So you're knowing that they're looking for an answer of a deluxe TV and a regular TV. You're getting in your head what kind of answer you're looking for helps you to set up the problem, okay? So write down the question that is being asked. And 3, you'll identify the variables from the question. You can kind of ignore everything else. Like if you know they're asking how many TVs of each type, your answer is going to be this many TVs of this type and this many of that. So what are the types? Those are your variables. So you know in here we want 2 answers, and one is a deluxe TV and one is a regular TV, so those are your variables. whatever it is you're looking to answer. Okay, so you identify the R and the D have to be the variables because that's what we're looking for, regular and deluxe. 4, we're going to make a table with the variables across the top. So basically, it looks like this. Your variables across the top and then total. Or, because sometimes they're going to have 3 variables. And that's when we need a different method to solve it. Substitution is, that's when you solve for like y, both equations, you rearrange them for y and then you set them equal to each other or plug one into the other.
Okay.
Yeah,
So
we're not really going to do that method, but you could, but our equations are never solved for y, so that's not going to be an easier technique.
Okay.
Yeah.
I'm just trying to remember, like, it's so.
But that is the other technique, yeah.
Yeah, okay.
So then we're going to fill in the tables. The table, sorry, from the question. And then we're going to write the equations. This is not a foolproof method, but it does help, especially when there's 3 variables, okay? So we'll see some exceptions to this, but basically it's the idea. If you identify the question, from the question you get the variables, then you can make a table and set up and put all your information in. If they don't have a total, you can't put that in the table, so you have to do it off to the side, but I'll show you that because there's a few little exceptions to that. All right, so if we go back to our sheet, number 2. So this says, a concert promoter needs to make $42,000 from the sale of 1,800 tickets. The promoter charges $20 for some tickets and $30 for the others. How many tickets of each type must be sold to yield the $4,200, or $42,000? So you read the question, you kind of get an idea of what it is. If there's lots of numbers in there, you will need to identify the question. What is they are asking? So they are saying, and you can just underline it. It's not really part of the answer, but we're going to write it down. Of each type. Oops, sorry. I'm writing the question from the first one. How many tickets of each type must be sold? So if you were answering the question right now with the full sentence, you would say, blank of the, what type of tickets are they? Right, they don't say like adult and kids, but they might, or ticket A and B, or main floor and balcony, like they could differentiate them. They don't, they just say some. So of the $20 tickets, and what are the other one? 30, and blank of the $30 tickets. Right, that would answer your question. Does that make sense? So those are your variables, the number of tickets. So let's call this one X and this one Y. Number of the $20 tickets is X, and the number of the $30 tickets is Y. So then we go and we put the numbers in the right columns or that they should be in, or rows. So then you go back to the question and then you get the numbers. So a concert promoter needs to make $42,000. So is that a ticket A, B, or combined total? It's a total. Altogether, they need to make 42,000 from the sale of 1,800 tickets. So this one's money, and this is number of tickets. And that's also a total. Right? The total number of tickets they want to sell. The promoter charges $20 for some tickets. So where would the $20 go? Well, the X tickets are $20 tickets, and this is the money column, or the money row. So 20 for X, and 30 for Y. So money, money, money. And that's it. Now, when you add the X's in here, so this will be 20 times the number of X tickets, right? That'll be the total money for X, and 30 times the number of Y tickets should add up to 42. This is just X and Y, because it's just the number of tickets. You add all the X plus all the Y. So our equations are like that. All right. And you don't need the table. You can jump right to the equations. That's totally fine. But sometimes when we have an X, a Y, and a Z, and you've got a whole bunch of numbers, the table will help organize the data for you to make the equations. Okay? So there's our two. And we can solve this. So how would we solve it? So this is set up. Set up. Sometimes on a test I'll say set up only, don't solve. Well, and then I'll give you a separate one to solve that's already set up, because if I say set up and solve,
So if you mess one up.
right, if you mess up the setup, then obviously the solve, and then your answers might not make sense. You might think you got it wrong in the solving part when it was actually the setup. So I usually separate it, set up this problem, so you would just stop once you get the equations, and then a separate question will say, solve this, and I set it up for you, right? Just because of that reason. If I make you go all the way through, and then you get stuck in the setting up part, you can't solve it. But we're going to solve these. So what would we do? Which do you want to eliminate? Maybe the X? Yeah, so let's multiply this one by minus 20. So I'm just going to write the first equation. And the second one times minus 20. Add them together. So Y is 600. And what would X be? So you can plug it into either equation. So obviously the last equation would be the easier one. So X plus 600 equals 1,800. So X is 12. So 1,200 of the $20 tickets and 600 of the $30 tickets.
Is that the only solution? Like,
Yeah.
it's weird, because you think there's more. Do you know what I mean? Like, to get that much money, you think that you could sell, say, more of the 30 or less?
Yeah, so these are, if you graph these equations, they look like that, and the point we're finding is where they both work. If it works in this one and not in that one, it's like one of these other points. You won't get exactly that much money.
Right.
Now, in the next section, after we do all these word problems and learn how to solve them all, we do more realistic ones. For example, they don't need to sell, maybe they need to sell exactly 1,800. Right, or they can sell 1,800 or less tickets,
Okay.
because maybe they only have seats for 1,800, right? But the money, they could make 42,000 or more, right? So the next section is, instead of all equal signs all the time, they're gonna be more realistic, so they want, only can sell 1,800, so there's a maximum number of tickets, but not the money. The money, they don't care, they could sell more, right? So then there's more possible answers that would work. Does that make sense? So that's what we're gonna do after, but these ones are all like, we wanna use exactly 42 buttons. We don't wanna use less than that, we want exactly, okay? All right, so number 3. A furniture manufacturer makes chairs, coffee tables, and dining room tables. Each chair is 2 minutes of sanding, 2 minutes of staining, 4 minutes of vernishing. Each coffee table is 5 minutes of sanding, 4 of staining, 3 of vernishing, and each dining room table, 5 of sanding, 4 of staining, 6 minutes of vernishing. The sanding and staining and vernishing benches are each available 6 hours per day. How many of each type of furniture can be made? So all of those numbers don't matter. You need to know how many variables and what the variables are, and that comes from the question. How many of each type of furniture? So what are the types of furniture? Chairs. We want the number of coffee tables. And we want the number of dining room tables. Right? So to answer that question, we would have a number for each of these. So this is going to be your X, your Y, and your Z. Or you could name the more appropriate things. But I usually just use X, Y, and Z, or X and Y. Okay. All right, so let's make a little table, and then we'll put all those numbers in. And this is a good example of when a table is maybe more useful to sort of organize all those numbers. So if we go back to the start, a furniture makes, okay, each chair, so which one's chair? This one? Each chair requires 2 minutes of sanding. Two minutes of staining, and 4 minutes of vernishing. All right, so now we've established what the rows are going to be. So the next one, each coffee table, so that's the Y, is 5, 4, and 3. 5, 4, and 3 vernishing. And dining room table is 5 sanding, 4 staining, and 6 vernishing. Now what are the totals? The total for sanding, the total for staining, and the total for vernishing. They say 6 hours each, but these are in minutes. So I would convert them to minutes. Right? You can't put hours and minutes in the same equation. So it's 6 hours, so what's 6 hours times 60 minutes? So 360. You could convert them all to hours, but then these would all be decimals, and that would, or fractions, and that wouldn't be good. Does that make sense? All right. Now, is that all the numbers? We're to the end? Yep. So the first equation is 2 times x, 2x plus 2y plus 5z equals 360, and so on. Does that make sense? This is 2 minutes for however many chairs they have in total, plus 4 minutes for, and this gives the equations for each machine. 4x plus, or each station, I guess. right? So the number of chairs times 2 minutes is the total number that they would sand. And then this is the sanding for the next item, and the sanding for the next item, and this is the total minutes they have for sanding.
Would it be 5 lines per station?
Oh, yeah, thank you. Yep, there. And I probably wouldn't have solved right. This is exactly why. You wouldn't want to then solve a problem if you had it set up wrong, because then it probably wouldn't work nice, then you wouldn't know where your mistake was. These ones we're not going to solve by elimination, we're going to solve using linear algebra, because it's a little long. Like if we went to solve these, you kind of eliminate the x in 2 of the equations, and then you have an x and a y, and you can eliminate the y in 2 of the equations, and then you have to plug one into the other, and it's way too much work, and it's really confusing which one you plugged into the other, and you have to do elimination, but it's like a combination. Instead of just one being eliminated, you have to kind of do 6 steps instead of just eliminating one. You have to eliminate them in pairs. So we're not even going to do that. So we're going to learn a new way, but we're going to just set up the rest of the ones on the question, and then we'll go back and learn how to solve them next class. Okay? So, number 4. And really, like I said, on the test, I asked you to stop here anyway, and then I would give you this problem with it set up for you to solve. 4. Bacteria of species A and species B are kept in a single test tube where they are fed 2 nutrients. Each day the test tube is supplied with that many units of the first and that of the second. Each bacteria, blah, 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 blah. Find the question. What populations of each species can coexist in the test tube so that all the nutrients are consumed each day? What populations of each species can coexist in the test tube? I don't need so that all the nutrients are consumed, because we want to answer the question, and answering the question would be this many of species, whatever the species is. What are the species? A, actually, and blank of species B. So if we had the number of species A and the number of species B, then that would answer our question. And you could use A and B as your variables if you wanted, right? Which kind of makes sense. It would keep them straight. So let's do that. So this is where you can kind of be confused, because the others, they talk about 2 nutrients too. First nutrient, second nutrient. But they don't want you to answer nutrients. They want you to answer the species. And it matters which one you have as your variables if you want to answer the right question. Just like the last one, we wanted chairs, tables, and tables to be the answers. We didn't want sanding, staining, and varnishing to be the answers, right? It can sort of go both ways, and one way would be the wrong way. They're not asking about that. They're asking how many tables, and not how many sanding.
Oh, like how much time is spent sanding?
Right, then that would be flipped, and they would, right. So you have to make sure there's usually right, and you need to, and the way to get the right one is to look at what the question's asking. So if we put A, B, total. All right. So bacteria species A and B are kept in a single test tube where they're fed 2 nutrients. Each day the test tube is supplied with, that's a total of the first nutrient. And this many of the second nutrient. Each bacteria of species A gets 2 of the first nutrient and 3 of the second. Each bacteria of species B is 1 of the first and 4 of the second. What populations of each species can coexist in the test tube so that they're all consumed? So this is only two variables, so we can solve it using elimination. So let's set it up. The table's not the setup, by the way. I'll take a mark off for not giving the equations. Okay? The table's just a method to figure out the equations. Right? But you need to actually take them out of there. So this would be 3a plus 4b equals 19,650. Does that make sense? Like, this is what I'm looking for. And also what A and B stand for. So this is where you get your marks, your variables, identifying what they are, and writing the right equations for it. Okay. This is showing your work. I could see what you did wrong if you had a table, but if you don't, if you jump right to the equations, that's also okay. All right, well, let's solve these. What would we eliminate? B, because we have to only multiply the first equation by -4. I should have written it up top. But so I'm going to multiply that one by -4. And I'm just going to rewrite that one. And then divide by -5. So there's A. There's the number of species of A. And to find B, just plug it into either equation. So say we took the 2A plus B equals 10,600 and put the A in. You could always check your answer by plugging it into both equations and make sure it makes sense. So it doesn't really say what the units of. I guess there are a number of those bacteria. I don't know. Yeah, we're almost done. Okay, so number 5. So, a company produces 4 combinations of mixed vegetables that sell in 1 kilogram packages. Italian style has zucchini, broccoli, and carrots. French style has broccoli, carrots, and cauliflower. Oriental style has zucchini, broccoli, carrots, and cauliflower. And combo style is broccoli and cauliflower. The company has a stock of that much zucchini, broccoli, carrots, and cauliflower. Lots of numbers. There's actually 4 things there, I think. How many packages of each style? So that's the question. How many packages of each style should it prepare? So what's each style? Italian style, French style, Oriental style, and combo style, 4 styles. So, Italian style, French.
This is like the number of Italian style.
Yeah, I think it's a number of packages, yeah, so number of Italian style packages. That's what we should write, number of French style packages. Oriental. And combo.
Kind of weird that the combo one has 2 of this one.
Yeah. I don't know who wrote this question. Okay, so XYZ won't work. Sometimes they'll go like this, X1, X2, X3, X4. Like, they'll number them and just pick one letter. You could pick different letters. You could pick, yeah, O's kind of weird, it looks like a 0, so it doesn't matter. But I want to show you that because you'll see that in books a lot. They do like a little subscript. So, I'm going to put them in the table that way, but I also want to write Italian, French. So I remember. Right? Now there's lots of different vegetables, so start with the first one. Italian style has zucchini is 0.3. Broccoli, 0.3, and carrots, 0.4. French style is 0.5 of broccoli, that's here, broccoli, 0.2 of carrots, and cauliflower, which we don't have listed, 0.3. Does that make sense? So this would be 0 cauliflower, and that would be 0, right? You don't need to put the 0, but it might help if you don't have these on straight lines. Oriental style is 0.2 of zucchini. Do we have zucchini listed? Yeah. Broccoli, carrots, I lost my place. 0.2 and 0.3 of cauliflower. So it has everything.